So welcome everybody to our Gamma seminar. Today we have the pleasure to guest Alberto Ibort from the Universidad Carlos III de Madrid and ICMAT, who is going to talk about from Heisenberg and Schwinger to groupoids and stacks. So Alberto, thank you very much for accepting our invitation. It's a pleasure to hear you, and the floor is yours.
Okay, thank you very much. Well, when I was thinking about this lecture, my main concern was that there was supposed to be, or part of the audience will be students that will be interested, or they will be willing to learn more in this fascinating, so to speak, subject between quantum mechanics and very abstract mathematical stuff. I've seen, because of the past lecture, that you have been exposed to groupoids and the algebroids and this kind of geometrical ideas recently. Last lecture, I think, was about the use of groupoids in differential equations. There were also a lecture by Rui Loja Fernandez on integrability, the integrability problem of Lie algebroids and Poisson manifolds. So here I'm going to give you another twist, another approach, or another another reason why groupoids play such an important role in modern physics and mathematics. Well,
Alberto,
yes, please.
sorry, let me interrupt you a while. We do it all the time, so please don't get annoyed.
No, it's okay. I mean,
We had a lot of mathematics. We had also Barsten, if I don't remember bad. But the missing thing is that we would like to hear something about the relation of these with, about groupoids, algebroids, and stacks with physics. This is the thing that it was missing. So we had a lot of mathematics indeed, and not much physics. So it would be nice to hear the applications you have about this topic.
Okay,
this is the thing.
so I think that probably I can fill this gap because my idea was to offer a panoramic way of why groupoids emerge and the natural way to describe quantum mechanical systems. And in order to do that, we will have to go back to the origins of quantum mechanics. So, well, this is the plan of the lecture. The first part, I will split that into three parts. The first one will be how groupoids emerge in the description of quantum mechanics. That is not a new idea. I mean, the formal way of doing that is been done by us recently. I mean, in the last, say, 5 years or 10 years, if you wish, we have been working on that. But it comes directly, or it drinks directly from the original ideas by Heisenberg. I will try to explain that in the first part. The second one, just to provide more context, I will tell you how the standard formalism of quantum mechanics emerged from the groupoidal picture or the groupoidal description of quantum physics. And the third one is something we are working on. It's not finished. It's I think some beautiful ideas which are emerging, and it's that groupoids is not enough to describe quantum systems. So we had to go to an even more interesting from the point of view of the algebraic and mathematical content, which is the theory of stacks. But they will be the last part. So let me begin straight away telling you we have to start in this, so to speak, travel that I want to walk with you, to travel with me together. We have to start with Heisenberg. So, as you know, in the year, actually it was 1925, Heisenberg published this fundamental paper that I'm not trying to tell the title, is in German, on the foundations and the basic new ideas that will lead to the new description, or to the correct description of the phenomena that were being observed at the atomic level. And the main idea there was that Heisenberg freed himself from the, so to speak, the change attached to classical thinking. Classical thinking was that, for instance, if you want to describe an electron in an atom, you have to make sense of what means the orbits of the electron. So people were struggling in the old times of quantum mechanics, what is called old quantum mechanics, how to keep the notion of orbits and but at the same time make it compatible with the experiments. And they were putting quantization conditions on the orbits and so on. So Heisenberg also they were retaining the idea of the phase space of the system, points in phase space, or volume elements in phase space, trying to attach meanings to that in the new, so to speak, physics that were revealed by the experiments. So Heisenberg got freed from that, and he was substituting its atomic, for instance, transitions were the main idea, and they were related to things that were happening in the sense that the basic or the primitive idea were that the atomic transitions were, so to speak, he was attaching quantities, physical quantities, let me call it MBA, to two different states of the system. So for Heisenberg, the main idea was that you have an atomic transition, the system is in the state A and later on is in the state B, let me call alpha this transition. You may have another transition from B to C, and then this is another transition. Eventually, he assigns a quantity MCB here, and then these two transitions can be composed, and you get here another transition, which is passing from the state A to the state C. And you get another, say, quantity that eventually you could test, you can construct, compare with experimental numbers, experimental outcomes, and that these quantities, they had to be related in a very special or particular way. And is that the quantity that you attach to the final process is going to be for each one of these two compositions, I mean, these two, this splitting of this factorization of this transition, this is going to be the product of these two quantities, MCB times MBA. And if you get rid of the intermediate step, what you will find is that the quantity which is irrelevant, or what you will is determined or is related to the experiments you were conducting, this MCA is going to be computed as the sum over all intermediate states of these quantities. So here you see the two main structures that underline the description of quantum mechanics. The primitive notions is not some abstract thing into a Hilbert space or linear operator or whatever, but the primitive notion in quantum physics is that of quantum transitions, we will simply say, that each one of these transitions have associated complex numbers, and that these complex numbers, they compose in a very specific way. Actually, they compose following a convolution law. This was an extraordinarily deep observation by Heisenberg. Unfortunately, he was mocked by, for instance, Pascual Jordan, who was saying, oh, poor Heisenberg, he didn't know how to multiply matrices, and he has discovered that what you are doing is you have two matrices, and a matrix M here, another one, and you get the product of the two matrices. So he was so ignorant that he didn't know how to multiply matrices. Of course, Heisenberg knew what matrices were. Remember, he was a German scientist, so he was very well educated in algebra. The main observation is that these matrices have a sense beyond the, so to speak, naive algebraic interpretation. They are functions defined in the modern language, we will say, on a groupoid, the groupoid of pairs of the states of the system. And that is a convolution law on the groupoid of pairs.
Well, so far with what you have said is a category. For it to be a groupoid, you have to
Yeah,
add invertibility.
exactly. That's absolutely correct. So let me continue. Let me elaborate. So this method and these deep ideas by Heisenberg that were also inspired by Niels Bohr, they were, so to speak, I wouldn't say forgotten, but they were put aside because of the impetus and the power of the formalism developed by von Neumann and Dirac. von Neumann introduced the theory of Hilbert spaces just to make sense of Heisenberg and Schrödinger descriptions at the same time. And this formalism and these ideas, which is again geometry in infinite dimensions by von Neumann, were so strong that immediately took over other approaches, right? More algebraic and in other direction. Dirac was the main, so to speak, amplifier of von Neumann's approach. And then these ideas or this way of dealing, what was called matrix mechanics, was in a sense forgotten, right? But in 1959, actually before that, it was Julian Schwinger that wanted to understand what he had been doing. William Schwinger, together with Richard Feynman and Shinichiro Tomonaga, they developed independently a complete or reasonable complete theory of the interaction between electromagnetic fields and matter. And under the name we call today quantum electrodynamics. It was the first quantum field theory that was consistent, at least at the perturbative level. And indeed, Julian Schwinger was the first one that was able to compute the first quantum corrections to the fine structure constants and many other things. And he was following a very, very original path, nothing to do, very different from the path that was following Feynman. Actually, Schwinger was first. But in order to do that, I don't want to enter into that. If you wish, I can tell you many more things about this, the motivation and the original ideas by Schwinger. But he had to, in order to make sense of the formalism that he was developing, they were awarded the Nobel Prize in 1965 because of that, was that the one most important Nobel Prizes in the 20th century. He had to review to create a new understanding of quantum mechanics. The standard formalism of quantum mechanics based on Hilbert spaces, linear operators, and all that was not good for his way of thinking about quantum field theories. So he started that road, he started to walk this road, and he came up with a new way of describing quantum mechanics, which was based on the notion of what he called selective measurements. Selective measurements. And what was that? Okay, so Schwinger's idea is that you can essentially, well, he wanted to obtain a language, a mathematical language. He wrote exactly in these terms, I'm using almost verbatim his words, that will capture in a non-classical, non-standard mathematical abstract language that will capture the behavior of the atomic processes happening at the atomic scale. And for that, he introduced symbols, and the symbols were of the following type. He considered that you have a system that, so before anything happens, will be completely determined. If you make measurements of this system, they will be completely determined by side quantities, A, and then after something happening to the system, some interaction with the system, or the system living by itself under its own evolution, it will pass to another situation wherever you make measurements on that will be completely determined by the quantities A prime. And he was calling these processes selective measurements and was using these symbols, M, A prime, right? And he was claiming that, of course, when you have two of these elementary processes, remember, this is exactly another way, a little bit more abstract than the quantum transitions that Heisenberg were using. Heisenberg was using quantum transitions, thinking mainly the transitions of electrons in the, so to speak, in the transitions in the different levels of energy of a given atom and things like that, because this was the natural realm that Heisenberg had in those days, spectroscopy, atomic physics, and things like that. Schwinger was thinking in something much more abstract, so he started to go beyond that, and he was thinking that we have so to speak, the fundamental things were processes, quantum things, that they were described by symbols. And the important thing, and this is what was remarkable in Schwinger's thinking, was the clear trace of a mathematical genius working on that, is that the important thing about the symbols were the algebraic properties relating them, not what they were exactly. And so he wrote that these symbols describing these, so to speak, primitive transitions, elementary selective measurements, he was calling them, they can be composed. So we can compose this symbol with the other one to give us a new transition, a new symbol, and that this would be exactly this one here. This partial composition, these symbols could only be composed provided that the outcome of the first will be the source of the second. So it was a partial composition law. He was claiming that this partial composition law is associative whenever three symbols can be composed. He claimed that there were units on that. I mean, there were these symbols composed on the right or on the left didn't change the output. So if you take M A prime composed with M A prime A, this was the same as the symbol M prime A, and this was exactly the same as M A prime A composed with M A on the right. And then he wrote the final property, and it was what you were commenting, some of you before, and is that if you go from A to A prime using the symbol MA prime A, and then there should be another transition, another symbol, another quantum process that will take you back to the original one. So this composition will be this unit. So you will find these equations exactly as I'm writing them now in a paper in the year 1959, the Proceedings of the National Academy of Sciences. Remember, Schwinger was a member of the National Academy of Sciences in the United States, so he didn't have to submit the papers. There were no referees, so he can publish whatever he wants. And then he was describing the algebra of selective measurements of quantum systems as families of abstract symbols satisfying this list of actions. But you recognize here that this is defining a groupoid. And this is our fundamental observation. So Schwinger introduced groupoids by means of the algebraic structure that some fundamental primitive quantum processes must satisfy. And including the existence of inverses, units here, and the existence of inverses, right? And associativity, of course. So our little contribution to all this was to simply, this was done with Florio Cialia, myself, and Beppe Marmo, in 2009, because of the insistence of Beppe Marmo of thinking or reading back the original papers and the original thinking by Schwinger, that to try to understand better, you know, Schwinger was extremely brilliant, but his way of writing was a little bit obscure. Indeed, he was dealing with notions and ideas that were not mature those days. Not only were completely unknown in physics, but not even in mathematics. You know, the theory of categories was developed by MacLean and Heisenberg, and the emphasis on the abstract approach to mathematics and the relations between objects provided by morphisms was a completely revolutionary idea. And in the 50s, the time that Schwinger was thinking about that, this was completely unheard of. I mean, no standard mathematician knew about that. much less a theoretical physicist like Schwinger. So it's not a mystery, it's not that these ideas or this way of thinking was, so to speak, completely obliterated, let me say, in this way. On the other hand, the extraordinary influence of Feynman did get the same results, but in a completely different way, and providing techniques and tools that could be used by anybody. The so-called, the famous Feynman diagrams and other perturbative techniques that didn't require to have a deep understanding of the things that were happening. They were not, so to speak, questioning you, what is the meaning of a quantum system and all these kind of things. There were tools that you can use and to go ahead. And so Schwinger was, in a sense, put aside, and the community, the scientists in general, not only physics, did not, so to speak, pay more attention to that. From time to time, of course, there was something, but not many more. So our own small contribution was to say, okay, this is a groupoid. So, and digging back about that, okay, so groupoid should be the natural structure that describes the primitive phenomena in quantum physics. And the primitive phenomena, yes, please.
Alberto, yes, a curiosity that I'm curious of that. Have you tried to apply all this groupoid stuff to some older interpretations of quantum mechanics? For example, I was thinking of the Wheeler equation, where time is can be understood as an entanglement. Yeah, there is no time relation. There are relations between states, transitions, and things like that. So it's your approach is nice because I don't see time at any place. It's just transitions and things like that. Have you tried to apply it to this stuff or other approaches to quantum mechanics? Because
yes.
it seems to be a quite faithful idea for this
yes,
kind.
Yes, of course. I mean, yes, we have been trying to systematically review most of the problems, issues, interpretations of quantum mechanics using, so to speak, let me say, ideas which are at the same time new, because they use, so to speak, modern categorical language, and which are at the same time very, very old. They come, this is what I was trying to emphasize before, from the foundations, the foundational moment of quantum mechanics. This is in the paper by Heisenberg in 1925, right? So last year we celebrated the 100th, the century of quantum mechanics. So these ideas are at the same time very modern, because we use something which is getting more and more popular in physics, in theoretical and mathematical physics, which is emphasizing the categorical approach, which is very well suited for physics, because physics is always about relations, right? Analysis, geometry is okay, very good, but if you wish, if you let me do that, I would say that category is a very, so to speak, higher abstraction of geometry. And so physics is about relations. So categorical language is very well suited for that. Analysis is very, so to speak, I mean, it's good because it allows you to crank numbers using coordinates and all that, but it's very far away from the spirit of physics, right? Where everything is about relations. So yes, we are systematically reviewing many, many aspects, including problems like, the long debates about the meaning of entanglement, superposition. Some of our papers discuss some of these aspects, but not everything, because we're okay.
Yeah, you need time, yeah. But it's interesting. Yes, it was that because it looks to be very well suited for third time problems to give a good. Okay, thank you.
We are balancing. Actually, we have a project that is being delayed, which is writing a big, so to speak, sort of summary of everything we know already about quantum physics using these ideas. But we are trying to move forward, because the real challenge, I mean, as I will show you in a moment, these ideas are very nice, and they provide a different understanding, deeper, I think, of quantum mechanics, and they solve some of the ambiguities and the apparent paradoxes of quantum mechanics, but they do not, at the end, produce new results. Because, as I will tell you in a moment, we will reproduce the standard formalism using Hilbert spaces and linear operators with a little work, right? So the real challenge is to go in the direction that Schwinger actually used that, and is in the direction of quantum field theories. And this means to write completely new foundations of quantum field theories using this groupoidal and categorical approach. And this will be where real progress will be, I mean, where you will get new things, right? Or where you will expect to have new things, apart from the pleasure of understanding things better, right? Which is always a strong motivation, okay? So let me summarize, closing this first part, by saying that our principle or postulate, so the principle, the groupoids principle, which is important to state, because we are going to see that in the third part, is that given a system, quantum system, of course, S, and any experimental setting let me call it E. We also call experimental setting a context for the quantum system. Then there is associated a groupoid gamma over omega such that the objects of the groupoid corresponds to the observations, the omega, correspond to the outcomes or observations of the experiments. And the morphisms or arrows they correspond to the transitions, to the observed transitions. Right, so in the first case, outcomes are the objects, and outcomes could be numbers that you get. So you have an experiment, you have a system. You're going to explore, to study, to interact with that system. For that, you will have a family of devices at your disposal. So you will have meters, you will have detectors, you will have lasers, you will have a lot clocks, of course. You will have computers, you will have wires. You will have a full laboratory. This is a context. Right? And then, because of that, you will obtain observations. The observations could be readings in some displays, they could be flashes, they could be sounds, they could be discharges of energy, so they could be anything, right? So the objects are actually points, elements of a set, right? Of course, our groupoids here, we do not have reasons to believe or to think that nature uses groupoids which are not small categories. But it could be, right? We are not close to that. And at the same time, in your experimental setting, in your context, in your laboratory, if you wish, you observe transitions. You observe that some electron is jumping from one level of energy another one and is emitting some radiation. So these transitions are the morphisms of the groupoid. And then the postulate we always have whenever you are, so to speak, extracting from the description of physical phenomena a mathematical model that eventually could become a law, you have always to make some little jumps. So saying that the composition is always, so to speak, defined, provided that so we have a partial composition law, of course, between composable elements in the groupoid, where these composable pairs of elements are transitions such that the target of the first equals the source of the second, where the target and the source of a transition is, of course, They are defined in the standard way. So of alpha equals A, provided that alpha is a transition from A to B, and that this composition law is associative, is something natural, that there are units for each outcome. There is the transition that means that nothing changes. So these are sort of natural algebraic completion of the observation we have. And there is the crucial issue that tells that you have a groupoid and not just a category, and is that for any transition, there is the inverse. This, you can argue about this condition. If this is necessary to include it or not. Well, we have been following the argument that we have to include this condition, the existence of inverses, because, and now I'm quoting the other guy, it was Richard Feynman. Feynman, in his thesis in 1949, he introduced as a fundamental principle of physics what he called microscopic reversibility. And it was that at the microscopic level, every process, every transition in a quantum system should be, well, this is our translation, sorry, that there was not a determined arrow of time. It was impossible to distinguish from, so to speak, forward evolution in time to backwards evolution in time. This was microscopic reversibility, quantum microscopic reversibility. And this was considered, and we subscribe to that principle by Feynman, right? That at the quantum level, there is not a distinguished arrow of time. So this implies that if there is a transition, meaning that there is a source that should be past in time with respect to a target that should be future in time, nothing distinguished, nothing, there should be no obstruction for the existence of the inverse transition, the transition that goes from, instead of from A to B, and go backwards in time from B to A. So this is the motivation of the sort of, if you wish, in a very quick description, the background for the groupoids picture. Whenever you have a system, you establish your experimental context, then there is a groupoid that extracts all the possible information that you get from all the experiments, measurements, determinations, etc., that you do about your system. And this is the groupoid you should study. This should be the backbone of the theory. The second, let me move into the second part, because if not, interrupt me if you have more questions. I know all examples. Before I move into the second part, let me give you some of the most, so to speak, conspicuous examples, right? So examples will be in a mathematics talk. Actual cases, actual situation will be in a physics talk, right? So examples will include finite dimensional systems, finite dimensional quantum systems, and they correspond to finite, to groupoids which have a finite number of outputs that we call A1 up to AN, right? And then the simplest groupoid describing that is the groupoid of pairs with the standard composition law. A, B composed with BC is just AC, right? Units are diagonal elements, and the inverse of the transition from A to B or from B to A is the pair in the diverse order. As we will comment in a moment, any groupoid, there's satisfying some additional conditions, has associated an algebra. For finite groupoids like this, the algebra is the algebra of matrices. And these are the kind of, so to speak, elementary, trivial quantum mechanical systems that were described, say, by Heisenberg in the original situation, almost, and which are used today in quantum information theory, quantum computing, everything, right? So the algebra of this groupoid is going to be the algebra of n by n matrices, where n is the cardinal, the number of elements of the set omega. The second one will be infinite dimensional systems, but infinite dimensional in the sense, in the restricted sense, that the space of objects, the outcomes that we are detecting with our detectors and with everything else we have, are given by a countable discrete set. For instance, natural numbers. For instance, you may think that we are studying a harmonic oscillator, and then we can detect the levels of energy of the harmonic oscillator. Then naturally, the space of outcomes for that system will be just the natural numbers, indicating which is the energy level of the harmonic oscillator of the system we are describing. And then the transitions are just given by pairs of natural numbers. So the groupoid again is the groupoid of pairs of natural numbers over itself. Now this system is very nice, is already non-trivial, but the algebra associated to this system is going to be the algebra of bounded operators on the L2 Hilbert space, so the space of countable sequences of complex numbers which are square summable, right? Which is the type 1 infinite factor in the classification, von Neumann classification of von Neumann algebras. These ones here, they were the type 1, the finite type 1n factor. More interesting are systems that exhibit symmetry. The way to exhibit
Sorry,
symmetry.
Alberto,
Yes,
one
please.
question. And
Yes,
you may have systems where the number of Q is, as you said, countable infinite discrete. For example, the oscillator, yeah? But the operator oscillator is not bounded. So how you could deal with such a thing?
Yes, well, of course, when we talk, this is the algebra, right, of the groupoid. When we construct the algebra, also in the standard picture, when we have a system which is described by a complex separable Hilbert space, then the algebra of this system is the space of all bounded operators. So unbounded operators are not elements in the algebra of bounded operators, of course, by definition. However, they have or they could have an important meaning. They could define quantum observables. There are two different ways of dealing with them. One is by means of considering if they are self-adjoint operators unbounded by considering the exponential of them. This means, because of the Stone-von Neumann theorem, the unitary group of the group of unitary transformations generated by it, which are genuinely in the algebra of bounded operators, or the other technique, which is sometimes used by people in operator theory when you work very formally with this, is to consider what are called affiliated operators to the algebra of bounded operators. So there are mathematical tricks to deal with them, right? But they are important. Indeed, in the construction of the von Neumann algebra of a groupoid, we will see about that, and I will tell you maybe a little bit more in a moment, okay?
Okay, thank you.
So I was telling you two more examples in order to, so to speak, this panoramic view, and it's when there is a symmetry group present in the theory. So, well, by the way, a group is a groupoid, so you can consider a system which is described on a group. These are many examples of interest in physics where you want to work directly with a group, right? And the system is described directly on the group. So this is another situation which is of interest. But more interesting is when the group is acting on some space, right? If omega is a measurable space and G is acting by measurable transformations, and if you have a measure here which is invariant under the action of the group G, you can construct, well, whenever you have an action of a group on a set, you have a groupoid, which is the semi-direct, well, which is the product, which is what we call the action groupoid, which is essentially the notation we use is that, which is as a set is just the Cartesian product of omega times G, and then the source and the target maps are just the maps sending the pair AG into A, this is the source, and sending this into the transformation if the group is acting on the left of the element A transformed by G. In addition, if there is some appropriate measurable structure here in this problem, you can construct, or the algebra associated to this groupoid is extremely rich. The algebra associated to this groupoid, I will maybe say something in a moment, that will be denoted by, in this way, is exactly what von Neumann introduced. It was called the group, the measure group of construction, and it's an algebra which is the algebra of essentially bounded functions and omega, the cross product algebra with the group G. This was von Neumann's structure. I'm not going to enter into the details, and this is the group theoretical approach. The interesting thing is that these systems, where you have symmetries, they have a very rich structure. And these algebras that we got, so this means these are, so to speak, a trace of the intrinsic complexity of the groupoids themselves, could be of all possible types, could be of type 1, type 2, and type 3, right? The classification of von Neumann algebras introduced or done by von Neumann himself. So there are plenty of situations here, very simple, among quotes, situations where you will get very interesting quantum systems. Finally, some Lie groupoids, which are relevant and we have been exploring recently. Probably the most interesting one is, suppose you have a manifold and you have a metric in this manifold, let me call it G. The metric could be a Riemannian metric or could be a Lorentzian metric. That means could be a semi-Riemannian structure. Then we have various groupoids here. We have the Riemann, what we call, this is our terminology, right? It's not completely standard. We have Riemann groupoid, and also we have what we call the Poincaré groupoid of that. The Riemann groupoid consists of all isometries between the tangent spaces of the groupoid. So the elements, the transition, the morphisms are triples: y, t, y, x, and x, where x and y are points in the manifold, and t, y, x is a linear map, it's an isomorphism from the tangent space into the point x into the point tangent space in the point y, and such that it's an isometry. This means that the pullback of the metric at the point y is exactly the metric at the point x. And the Poincaré group is defined in a similar way, it's a little bit more richer. The nice thing is that these groupoids, they are finite dimensional Lie groupoids. They have a canonical, natural, smooth structure, which is compatible with all the operations. And they are instrumental in the study of the fundamental symmetries of physical systems. You were asking at the beginning about physics. Well, we have proved, and has been published this year, a couple of months ago, that the program of classification of elementary particles in curved spacetimes could and should be done using the theory of representations of these groupoids. Just to give you a little more context about that, we have the fundamental theorem by Wigner, was one of the most relevant papers, was published in 1939, Annals of Mathematics, where Wigner proved that the unitary, projective, irreducible representations of the Poincaré group were characterized by two numbers, the mass and the spin. And this provided the first clear and unambiguous classification of elementary particles. Particles, they are elementary particles, they are classified at first by the irreducible projective representations of a group, the group of symmetry of Minkowski spacetime, which is the Poincaré group, right? However, well, if you add other symmetries, inner symmetries, and so you get further classification of particles, introducing additional quantum numbers coming from the classification of those representations, right? But the two fundamental quantum numbers, or the two first numbers that appears to classify any particle, which is its mass and spin, they are simply in correspondence with, or they are labeling, they are describing the irreducible representations of a group. a group which is acting on Minkowski space-time. So we have an action groupoid. We have the situation 3, right? Now the key observation is, or the key problem that has not been solved in all these years is, well, what happens when the space-time is curved? It's not flat. It's not Minkowski. In general, for any generic perturbation of Minkowski space-time, the group of global isometries, the pleomorphisms of your space-time that preserve the metric, is trivial, right? The group of isometries of a generic space-time contains only the identity. Only a few examples, which are very symmetric, so which are homogeneous spaces of groups, like the Sitter and the Sitter space-times and others, they have rich groups of isometries, Minkowski, others, right? But for a generic space-time, there is no group of isometries. So how do we make sense of the meaning of elementary particles? On the other hand, we experience the existence of elementary particles in our environment, which is clearly unknown. It's not flat, right? We are in a potential well, we are in a gravitational well, right? There are particles. We see systematically electrons, we manipulate electrons and many other particles, protons, whatever, right? So why are there if there is no Poincare group? Where do they come from, right? Well, the key idea is that they correspond to representations of the canonical groupoids associated to your given space-time. Any space-time has various groupoids, the Riemann one that I was telling you, another one which is a little bit richer is the one we need, we call it the Poincare groupoid, and the representations of that groupoid classify elementary particles on your given space-time. This is a little, so to speak, physics contribution to this discussion. So let me see how much time do I have. Okay, I have only 50 minutes. So let me jump into the third part, because probably you will want to learn about how stacks appear in all this stuff. So the section 2 was about observables and states. Here, let me give you the very rough sketch. If you have a groupoid, then what you would like to construct is the algebra of observables of the theory, which is being described by this groupoid. This algebra of observables is some completion of the algebraic algebra of the groupoid. So associated to any groupoid, to any group, to any algebraic structure with an associative composition law, you can construct this algebraic algebra, which is, let me denote in this way, C of gamma, which is the family of formal linear combinations of elements in gamma. So they are elements of the form where A alpha is complex numbers. So this finite linear combination, these sums here, they are always finite, they carry a canonical algebra structure. You can multiply these two by taking compositions of these two guys. You have a star here, thing here, and you can introduce norms, natural norms in this space. Now you can complete these algebras, and the completion of these algebras, doing it properly, to the appropriate norms, is going to be what is called, or we call, the von Neumann algebra of the groupoid. There is a very natural, a very nice way of doing this construction, which was done by Alain Kohn in the year 1979. He was trying to understand the structure of what he called singular spaces. By that, he meant spaces that had very bad properties from the point of view of standard topology or standard measure theory or standard differential or analytical analytical viewpoint. For instance, quotients of sets by foliations. Imagine the quotient of a cycle by an irrational rotation, right? This quotient is very bad because it's non-Hausdorff. There are no invariant, there are no induced measures there in the bottom. Everything is an atom. I mean, there is no way of distinguishing two different irrational rotations. Using standard measure theoretical, algebraic, analytical, or geometrical techniques. So the idea by Witten, by Kohn, my God, by Kohn was how to analyze singular spaces. And his brilliant idea, of course, was we don't have to look at the quotient, we don't have to look at the space. What we have to do is to unfold it using a groupoid structure, and then developing new invariants at the level of the groupoid. For that, he created what he called a non-commutative theory of integration. That is nothing but a theory of integration in groupoids adapted to the algebraic structure of the groupoid. Using this way of, so to speak, integration on groupoids, he constructed what he called the algebra of the groupoid, which is a von Neumann algebra, and it's the algebra I'm telling you. We identify this algebra with the algebra of bounded observables. The beautiful thing about this is that this algebra can be seen as functions, well, a completion of an algebra of functions on the groupoid. And these functions, they should be self-adjoint in a natural sense. We define the star of a function as definition, alpha minus 1 complex conjugate. And so the functions on a groupoid, which are self-adjoint, such that this is alpha, they provide a natural notion of observables in this setting. Now, there could be bounded observables, provided that these functions, they define bounded elements with respect to the induced norms, so they are in completion, or there could be unbounded observables, as you were asking before, right? So there is a natural way of thinking about all these things at the groupoid level, and without, so to speak, the complications, let me say in this sense, coming from functional analysis on the spaces of operators on Hilbert spaces, because they are actually functions on the groupoid, right? And so geometry is much more, so to speak, closer to you than when you jumped into Hilbert spaces. Once you have the algebra of observables, then you define states. Well, there is a natural notion of states. We do not define states. They are there, right? We are not inventing things. We are discovering things. So states are natural ingredients on algebras, right? Both from a mathematical viewpoint or from a physical viewpoint. Because the states, they are just linear functionals, which are normalized. So the unit element goes into one, and they are positive, right? So they map positive elements into positive numbers, right? Then positive normalized observables that provide the expected value. So you have an observable A in your algebra, row of A is just the expected value of the observable A in the state row. This means that you go to your laboratory and you start measuring the observable A, whatever it is. Once your system has been prepared in the state row, the statistical average, so the average of the numbers that you get in your laboratory, they are exactly the value that the linear functional row takes on A. So this is the critical identification between physics here on the right, mathematics here on the left. Right? So states are completely natural, both from the physical side, from the mathematical side. Now, whenever you have a state row, there is a natural construction called the GNS construction, Gelbart, Neymar, Sigal, that associated to any state associates a Hilbert space, right? A vector in this Hilbert space, fundamental, reference, background, ground vector, vacuum vector, whatever you want to call it, and a canonical realization or representation of your algebra of observables onto your Hilbert space. So pi rho goes from the algebra of observables of the theory into the algebra of bounded operators on row H, and H row, sorry. This GNS construction is what allows you to recover the standard formalism of quantum mechanics. There are a lot of things can be said about that, sorry. do not have time for that if I want to say a couple of words about the third part. So let me jump right away into stacks. So the problem, well, this comes because of a problem. It is the many-groupoids problem. Of course, remember in my scheme before, we have the system. And then for any environment or context, this is the system we want to discuss. We get, say, a groupoid that depends on this context. This is the groupoid, right? But if we change the laboratory or we change the devices we use to explore, to interact with our system, we are going to change the groupoid. So associated to the same system, there is going to be a plurality of groupoids. Even worse, some of these groupoids, they are going, because you may say, okay, the groupoids, maybe they describe some fundamental, so to speak, description of the system, but at the end, we can deal, or we can live just thinking about the algebra of observables and states and all that, so much closer to the standard formalism. What happens is that in many occasions, these groupoids that lead to the same or isomorphic algebras of observables. Let me give you an example. For instance, consider that we are describing the harmonic oscillator, right? Again, so we can organize, or we can have a laboratory when we are exploring exactly, or we can detect, we are doing a spectroscopy, so we can see exactly what are the energies that the harmonic oscillator is radiating when it's jumping from orbit to orbit. So the groupoid description for that experimental context, the spectroscopy, would be the groupoid of pairs of the natural numbers I was telling you before, n times n. But we can be using something completely different. We have a system that is behaving like a harmonic oscillator on the real line, on one dimension, for instance, and instead of looking at the energy levels, we have detectors telling us where the particle is, right? The particle is in a potential well, which is parabolic, and then or near equilibrium, if you wish. So the first order is going to be a parabol, and then we are able to detect. So we have a detection system here. Now the space of outcomes for this system will be the positions in the real line will be R, and the natural groupoid to describe that will be R times R, the groupoid of pairs on the real line. The algebra of the first, in the first case, is going to be the algebra of linear operators, bounded operators on L2. And the algebra of the second is the algebra of bounded operators of L2 of R, of the Hilbert space of square integral functions on the real line. But these two algebras, these two von Neumann algebras, they are isomorphic. They are the type 1 infinite. So the algebras do not resolve the information about the different scenarios. It's very difficult to understand how different scenarios, how different contexts will appear inside the algebras of some sort of, say, big algebra that contains everything. So we should retain the many groupoids description of the system. But of course, the different groupoidal descriptions of the system, they cannot be completely unrelated because they are at the same time, they are describing the same physical entity. The system we are describing is all the time the same. Could be an electron in a box, right? So we can use different systems to interact with it. We can use lasers, we can put electromagnetic fields, magnetic fields there, we can put detectors, we can put walls inside, so we can do all kind of tricks with that poor little electron, right? Each one of these things we do will provide a different context. So the problem, the many-groupoids problem, is how to organize the information which is gathered using the different ways of working with the with the system, right? The different context. So, and this is and for a lot, we have been thinking on that for quite some time, and then we came with the following idea. Of course, the 2 more minutes and I'm done. The question is, what is a system, right? So if you try to think that this is some kind of primitive notion that we have a system, immediately you see that you enter into circular arguments. You cannot define what is a system by itself in physical terms, because a system should be something which is, so to speak, isolated, independent of the rest of the universe, something that has its own identity. But whenever you want to describe that system, you have to interact with it. So this means that the system cannot be isolated. It should be in some way of interaction with some external, the rest of the universe where you are living, the person or the agent that is trying to describe it. So the way to avoid this circularity is, which is a nice idea with a long mathematical tradition, is that in order to describe something in mathematics, we don't need to describe the thing directly. We don't have to provide an intrinsic definition of it. We can use an implicit definition. We can use a definition of that thing, of this mathematical thing, in terms of how this thing interacts with the rest of things. This is categorical thinking. So instead of thinking that we can describe the system by itself, it's much better to say that the quantum system is the family of all possible contexts. This means a system, I repeat, this is the abstract notion, a quantum system is determined by the properties of all possible experimental settings that we can use on it, of all possible contexts. And this context, they can be organized, it will take a little bit, as a category. We call it the category of contexts. Actually, more than that, the different experimental settings, the objects are going to be the experimental settings, and the morphisms are going to be the translations between them. I could provide you more examples, but it's a category. This category is actually, in technical names, has to be, because of physical reasons, a site. A site is a category that carries, for those of you that know about that, about topos theory, is a category that carries what is called a Grothendieck topology, or actually a pre-topology. This means that where it makes sense to talk about covariance. The reason about that, to introduce that, is that suppose you have an apparatus, a device that is measuring the position of a particle. That is going to be an experimental setting corresponding to the technology, for instance, of 2026. Now, we buy the best possible detector which is available in the market, right? This detector is going to have a resolution, say, of 1 micron or 1 nanometer, right? Whatever. It's going to have a finite precision. So the outputs of the experimental setting corresponding to this technology is going to be this subset, these balls, so to speak, if you wish, in Euclidean space, right? But in a little while, in a couple of years, or in 6 months, or in 10 years, there could be detectors which will have twice a resolution which is twice the one that we have today. We have a much more refined way of doing that. So it is clear that the technology of today, the context that we have today, will be or could be covered by technologies that will happen or will appear in the past. We don't have to think in this, so to speak, timely way. We can think that simply we can use for some experiments devices. We have some, so to speak, resolution, so they provide outcomes which are some given sets, but we can take, for instance, to understand, to discover the properties of the property, we could take a coarse-graining approach. So we can put these sets together, getting a more grainy picture. and so on. So there is a natural notion among, or there will be a natural notion among technologies of coarse graining and refinements. And this corresponds nicely with the notion of sites, coverings. So the space of context, which is what defines implicitly our system, is a site. And what we have is that to any one of these sites, to any one of these contexts, the objects in this category, we associate a groupoid. So we have an assignment from environments to groupoids. And this assignment is what technically is called a pseudo-functor, in the sense that when we have the composition of two morphisms here, so to speak, the groupoids which are going to be equivalent to the one which will correspond to the composition. Pseudo-functors from sites into the category of groupoids is exactly what are called pre-stacks. And now, if you want that the description provided by all these contexts will be coherent among them, when we will transform one into the other, when we will translate information from one to the other, and that local information could be put together, glued to get something global, then this is exactly the definition of a stack. So here, the final message is that we will recover the notion of stacks from physical conditions on the experiments we can perform on quantum systems. That will be, so to speak, the bottom line. Sorry by extending my time. I will stop here. I know that there is a lot of questions to discuss and so on, so I'm open to anything you may ask, or to keeping the discussion going on in private after the talk. So thank you very much.
Thank you very much, Alberto, for a nice talk. This is what it was missing, to talk about physics, about category theory, about groupoids and stacks, because we had a lot of theory, but so far not as much physics. It's cool. So
it's a nice source. Everything that I'm saying, I've said, is a nice source of non-trivial examples for stacks. For instance, if you are people which are in stacks theory or categorical thinking, it's a very nice, so to speak, it's a mind goal to dig for non-trivial situations, examples, and applications.
Yeah, but you know, Alberto, that it's for a long time, this is a quite controversial topic, because many people have thought of category theory and physics like something like, it's a good language, but does nothing. Yeah, I mean, it's just a nice way of saying things. This is something you can easily find. Indeed, if you come here and you talk about what you said, you will have to convince everybody that, well, that is worth it. Yeah, that you can do something about physics. So it's nice to see that someone is working on it and looking for nice examples and nice theory.
Let me tell you, I didn't have time, but the next step will be to give you an example of this, right? To construct this one stack, one explicit one. And the first one to do, which is already non-trivial, is for the qubit. For the simplest two-dimensional system, when you follow this program and you construct the stack, you will find that this is highly non-trivial. And actually, we are working on that. I mean, this is, so already the simplest non-trivial quantum system provides interesting mathematical objects. Anyway, so the stack you get is related with what you know is called the theory of gerbs, and that is a non-trivial gerb on the sphere, and this is the one that appears in the case of the qubit.
So there is one question, Alberto, because you know there is just 1 hour, unfortunately.
Yeah,
there is
I'm sorry, I had to compress.
Yeah, I mean, you don't need to be sorry. I mean, it's an hour. It's everything we had, and you have made a lot of it. But you know, can you recommend some literature about this topic for people to read? Because you know, after the talk, normally we take a look at it, and sometimes it's the people have topics for people to work on it.
Some of our first papers are quite readable, because they were, you know, we were exploring the situation, so we were not so much formal. We were putting a lot of examples. Some of the hard, so to speak, functional analysis was so to speak, put under the carpet because we were considering always discrete, countable situations. So I think our original papers, 2019, which is, they are called like that. I mean, they were a series of 4. Later on, we did some more technical stuff, right? But the original 4 papers is the Schwinger picture of quantum mechanics 1, groupoids. It was the first one when we introduced the groupoid. And then we were doing, so to speak, translating Schwinger into groupoid, modern groupoid language. This was the first. The second one was Schwinger picture of quantum mechanics 2, and it was observables and states, where we were discussing the construction of the algebra of observables, again with plenty of examples and that. And so on.
These worked, sorry, Alberto, these works were on the archive, yeah?
Yes, they are all in the archive. Yes,
okay.
yes.
Because from a practical point of view, if you don't mind, normally in the web page we put some slides, but you have presented this on the Blackboard.
Okay. I have prepared some slides. I can pass it to you if you want. I don't know if you want to.
Yeah. I mean, the thing is that if you have some literature on it, for example, it would be nice to have it.
These references that I was telling you a moment ago, they are there, so you can.
Oh, that's so cool. Yeah, I mean that good because we used to publish it on our website. If you don't mind, we can put it.
I will send it to you.
I will let someone else to say anything. Okay. Okay. So, is there any question, remark, comment to our speaker? Otherwise, I could talk to him for a while. We don't have so much time. So, please go on.
Well, it's very, very nice and very thought-stimulating talk, as all of your talks, Alberto. So thank you. Well, I don't have any question, just to remark that I like that you emphasized how physics is about fundamental relations, which is somehow opposite to this idea in quantum mechanics of set up and calculate, that there's some idea of theoretical physics from maybe the times of Feynman and so on, that physics is just some obscure machine that produces a number, and the more decimals that number has, the better, but how it works, that's a secondary thing, and that's somehow opposite to what you suggest.
Yeah, you know, the problem is that this machine, the obscure machine that produces numbers, which is correct, this is always motivated and founded into some deep idea, right? People tend to forget about the idea and use just the machine, right? But if you want to make real progress, you have to go beyond that original idea, right? So in quantum field theories, apart from the developments in gauge theories, was the introduction of serious geometrical differential geometry, bundles, connections, and all that, we are still depending on the ideas led by Schwinger and Feynman. Mostly Feynman, because as I was telling you, Schwinger has been procrastinated for various reasons, right? So there's been no real progress. I mean, all this stuff about, I don't know, string theory and so on. So this is not real progress to respect to the foundational ideas that were used already in the 50s, right? Apart from the use of heavy, differential geometry, that I acknowledge, right? But on the quantum side, properly, there's been no really improvement about that. So this is why we are stuck with quantum gravity, right? There is no real advance in that direction, right?
Yeah, for sure.
So you see.
I could make some comments, but I prefer to let our participants to take part. So is there any other comment, Mark?
Well, you mentioned the classification of the particles. Using this approach, you retrieve this classification, or you will get something more?
Well, both. I mean, we recover Wigner's classification of, we proved in this very recent paper that I was telling before, that for a large class of space-times, the irreducible projective representations of the Poincare groupoid of the space-time, they are classified by the classification of them includes the Wigner's classification. There is mass and spin, And there are also the particles that were, so to speak, predicted by Wigner that were never been detected, what they are called continuous spin representations, right? What sometimes is called the last Wigner particle that will never. There's always been some, waving hands saying why we don't see these particles that should appear if all irreducible projective representations of the Poincare group would make physical sense. Why they have not been detected, but the final reason, as Weinberg said once, is that they have never been detected. So they are not physical because they have never been detected, right? So period, right? Well, so we got the mass spin, the continuous spin representations, and a new family of representations that were not in the original classification by Wigner, that corresponds to a sort of internal momentum, angular momentum variable, mu. And they come from non-trivial representations of the Heisenberg group. Of course, in order to show you that, I will have to go through all details, which will take quite some time, but I can explain that to you if you wish, or you just have a look at the last part of our paper, where the construction of representation. So we reproduce the classification for a large class of spacetimes, which is good. So there is no obstruction. In curved spacetimes, there are particles, elementary particles, good. This agrees with the experience. And we predict another family of particles. That they correspond to new physics is questionable because even the continuous spin representations of the original Wigner work had never been seen. So I'm not claiming that we should go jump into and detect these new or observe these new particles, right? But they are there. I mean, they are mathematical consequences of the theory.
Okay. Thank you very much.
You're welcome.
And could you share with some future directions with this approach?
Sorry, if we are.
Yeah, could you tell us something about like future work
Oh,
with
yeah.
this approach?
Oh, yeah. You mean in the classification of particles and the use of this kinematic relativistic groupoids, or the general philosophy of groupoids?
More like maybe general philosophy, but I would like to hear both, to be honest.
The main thing that we will, I mean, and I will personally would like to do, will be to understand, to reconcile Schwinger approach to quantum field theory with the Feynman one. I mean, to try to, I wouldn't say, because this will be preposterous to claim that we could make a breakthrough in this direction. But so at this moment, there is, I mean, you can go Feynman's direction, perturbative Lagrangian relativistic quantum field theories, where you use classical Lagrangian. When you compute amplitudes, in Feynman's approach, you are using a classical background. You are using a bundle over a classical spacetime, a Lagrangian density there, and then you do whatever, right? That you do Feynman. However, Schwinger was much more profound, and for Schwinger, the Lagrangian was not a classical Lagrangian, was a quantum operator. So he created, actually, he wrote, or he computed his corrections to quantum corrections to the finest structure constant I was telling you before, using a quantum variational principle. He wanted to, so to speak, jump from classical to quantum and extended the basic idea in classical Lagrangian mechanics that will tell you what the equations of motion are from an action. So what he did was to derive, to write an equation actually for the amplitudes using a quantum variational principle, where the Lagrangian is a quantum operator. From there, I mean, the equations were so complicated and difficult to handle that it was his student, Friedman Dyson, that put these equations in a, so to speak, more appealing or palatable way, and they are known today as the Dyson-Schwinger equations that cannot be solved. I mean, they are so complicated that they can be solved in very, very, very particular instances. We do not have, so to speak, shortcuts or tricks like Feynman diagrams and so to handle them, right? But the complicacy of the equations is coming afterwards. I mean, there is a fundamental idea before that, and that there is a quantum variational principle that handles or gives rise or allows you to understand the behavior of the quantum system of fields. And this has never been, so to speak, understood, I think, properly. And we would like to go forward to understand that better and to be able to analyze, of course, things that have been done already, like QED and other things. Of course, we are not going to get anything better than what would have been done, right? But in problems, for instance, in non-perturbative problems, this could be a real way forward. When you cannot use perturbative analysis of any kind, then you have to rely on fundamental principles. And fundamental principles, they are not ready, but thinking back, using this new, so to speak, or more modern mathematical, let me say, more mature mathematical view, we can go back and encode, right, and Schwinger, and to put into the 21st century. And this could be something that I will be very glad to do. So we are trying to do that. We are trying to revisit field theories from this categorical approach. Of course, there are many works. I mean, many people using categorical techniques in field theories and different states, in different ways and so. But from combining the native quantum ideas, that's the new thing, right? Because quantum ideas can be framed in categorical groupoidal language, and then you insert that in whatever other development you do. This is sort of one of the main directions, the one that, so to speak, touched me closer, right? And that I would like to do some contributions. But okay, yeah, that's.
Yeah, thank you very much for your answer and for a very interesting talk.
You're welcome.
Okay, is there any other question, remark? No, so just a quick remark, yeah. Your idea of using groupoids to describe relations between the states of the systems, it's something that is going around right now. I mean, it's not solely what you are saying, it's something very new that people are considering, yeah. But the groupoid approach seems to be a quite nice way of doing it, yes, to see at least.
It's natural. I mean,
yeah. I mean, it's quite natural, and it seems that it's quite compatible with this idea that you said. It could be a nice advance to give some language that solves some theoretical problems to understand. So it's quite cool. The other thing is that, yes, a quick comment, and we finish because we're running out of time. You were talking about experimental evolution and things like that with quantum mechanics. There are a nice experiment-based, well, they are thinking of it, a theoretical experiment given by Penrose in a paper a long time ago published. It was something like on the gravitization of quantum mechanics or something like that. And the thing is, more or less, if I quite remember it properly, it was something like, if you respect the equivalent principle when you have several gravitational fields, you will need several different types. And due to that, they will appear different phases for your solution. Nevertheless, if you respect quantum mechanics, these both things, they have to be equivalent. As a consequence, there are measurements of the wave function of this problem that they are very, very small. It depends on time, on the factor that goes to this. I think that it was to the third power, something like that. It was very small, and it was about what it has to be true: quantum mechanics or classical mechanics, the principal equivalence of quantum mechanics. They are about to measure it. I mean, this is very close. It could be nice. I remember it that maybe could be interesting. Apart from that, I could say that I have many questions to you, Alberto. That's after this. I mean, how to go to classical mechanics, for example, how you can deal with all the topics, how to your example about stacks. But okay, it was nice. Thank you very much. It was a pleasure.
You're welcome.
So Xavi, can you finish the recording?